The next molecules that we'll be looking at are the nucleotides, which are basic monomeric units of nucleic acids. So you can consider a nucleic acid as a stretch of beads joined by a thread. So these beads, they are the nucleotides. The thread what we have here is basically a covalent bond called phosphodiester linkage. So you have two ester linkages involving a phosphate group. That's why it is called as phosphodiester linkage. So a nucleic acid is nothing but a polynucleotide chain having phosphodiester linkages between the monomeric nucleotide units. Since it is ester basically, we can also call a nucleic acid as a polyester. When you take the nucleic acid, either DNA or RNA, and when you subject it to acid hydrolysis, the acid hydrolysis will break down all phosphodiester bonds so that one nucleotide gets separated from adjacent nucleotide. So you get free nucleotide. This free nucleotide is phosphate ester of a nucleoside. So now we are getting two components in the nucleotide. One component, the phosphate component, which is inorganic component having a negative charge, and the second one, a nucleoside component containing a sugar and a base which is neutral. So we'll divide the nucleotide into phosphate and nucleoside. The phosphate has a pKa value, dissociation constant, that is close to 1. Since the dissociation constant is so low, it will have negative charge at physiological pH. In other words, a nucleotide and a nucleic acid, they will be negatively charged and acidic in nature because of the phosphate. So it is phosphate that's responsible for acidic nature of the nucleotides and nucleic acid. It is a phosphate that is responsible for the negative charge associated with the nucleotides and nucleic acids. Phosphate is polar. It is hydrophilic. We can divide into two components. The first one, the sugar. Second one, nitrogenous base. The sugars that we have in case of nucleotides and nucleic acids are 5-carbon aldoses. So we call them as aldopentoses. They exist in beta anomeric form, which is more stable. They have D configuration, which is true with most of the naturally occurring sugars. They exist in 5-membered ring structures. That's what we call it as furanose forms. The furanose form is 5-membered ring structure. We have two kinds of sugars in nucleic acids. One is ribose. This occurs in RNA. Second one is 2-deoxyribose. This occurs in DNA. And this particular property, we take it as the fundamental difference between the RNA and DNA. If the sugar in a nucleic acid molecule is ribose, it is RNA. If the sugar is deoxyribose, it is DNA. In other words, this is the fundamental difference between RNA and DNA. You may have any other differences, like RNA is usually single stranded, DNA is usually double stranded, RNA usually contains uracil, DNA usually contains thymine, RNA usually not acts as a genetic material, DNA usually acts as a genetic material. For each one of these differences there are exceptions. But in terms of the sugar, RNA always contains ribose sugar, DNA always contains deoxyribose sugar. The two sugars differ only at one position. So this is the furanose ring form. So this is beta configuration, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. This is the anomeric carbon. So this compound we call it as beta D ribofuranose. Most commonly it's called ribose. It is found in RNA. Now the important thing is this one. At second position contains hydroxyl group. The other one has exactly the same structure except for second position. So this position it has hydrogen. It is deoxy. And deoxy position is 2. So it lacks oxygen. So this is the one that goes to the ribose. This is the one that goes to the deoxyribose. Because ribose has 2 hydroxyl groups here, it can undergo cyclic structure formation. That's why when you use alkali like sodium hydroxide, RNA will be subjected to hydrolysis. Here, the chances of cyclic nucleotide formation is less. Practically you don't have it because this has no hydroxyl group, and therefore DNA is alkali stable. So RNA alkali labile, DNA alkali stable. Now these 2 components, the sugar and the phosphate, which are polar hydrophilic, form the backbone of a nucleic acid. So they will be present on the outside. In the inside, you will have the nitrogenous bases, which are hydrophobic. So the nitrogenous bases, they are aromatic. So that means they have the delocalized pi electrons. They are heterocyclic. That means in addition to carbon in the ring structure, they also contain nitrogen atom. They are hydrophobic, so they like to be inside a molecule rather than outside the molecule. They try to keep away from the surrounding water. They are weakly basic, so normally we don't see any charge associated with the base. The bases will be 0 charge. They don't get the positive charge. They are located in the interior of the molecule. They absorb, this is an aromatic property. All aromatic compounds have the ability to absorb UV radiation. So these absorb UV radiation, having maximum absorption wavelength as 260 nanometers. So nitrogenous bases have lambda max 260, aromatic amino acids have lambda max 280. Then when you take the nitrogenous bases, we can further divide them depending on how many rings they have. So the nitrogenous bases may have a single ring, the nitrogenous bases may have double rings. So we have 2 distinct types. The nitrogenous bases having single ring are called pyrimidines. Whereas the nitrogenous bases having double ring are called purines. So a purine ring is a combination of two rings. One is pyrimidine ring. So we always get pyrimidine rings plus a 5-membered imidazole ring. So this combination of pyrimidine ring and imidazole ring is what we call it as a purine ring. Imidazole ring also occurs in histidine, the amino acid. Now if you take the purines in terms of numbering, the conventional numbering is this. So that is pyrimidine ring. This is imidazole ring. So we number this one from here 1, 2, 3, 4, 5, 6, 7, 8, 9. This 9th position forms glycosidic bond with C1 prime of sugar. So 9th nitrogen will be forming a bond with first carbon of the sugar. It doesn't matter whether it is ribosugar or deoxyribosugar. This position determines whether the base is amino or keto. Amino or keto substituent. If you have amino group, then it will become aminopurine. If you have keto group, then it will become ketopurine. Here, sometimes, not compulsorily, sometimes amino or keto group occurs. So this is the structure of a purine ring. If you take the same in terms of the pyrimidine ring, which is relatively a simple one, so that's a pyrimidine ring. This time we number from the nitrogen and then we'll move in clockwise direction. So we get 1, 2, 3, 4, 5, 6. This first position forms glycosidic linkage with C1 prime of sugar. So carefully see that in purines and pyrimidines, the sugar's C1 will not be changed in glycosidic linkage. It is the base nitrogen that will be changed. It is 9 in the case of purines, 1 in the case of pyrimidines. This position always contains keto group. There is no exception. Every pyrimidine base at second position has a keto group. This position determines whether it is amino or keto pyrimidine. So you may have amino base or the keto base based on the substituent. Then the fifth position can be methylated sometimes. So we have thymine, for example. It is methylated uracil. You have 5-methyl cytosine. Now important thing that you have to remember here is this methylation does not change the base pairing property. So you get the same base pairing property. So that's in terms of the purine ring and the pyrimidine ring. Then we'll take the common purines and pyrimidines. So first we'll go to the purines. We have 2 purines that are common, which occur both in DNA and RNA. There is no purine based difference of nucleic acids. So this is adenine, which we call it as 6-amino purine. So it is amino base. It is the other purine. It's a keto purine. Having an amino substituent at second position, keto substituent at sixth position. This we call it as guanine. So 2-amino 6-oxo purine or a keto purine. So these two occur in DNA and RNA. So there is no separation when it comes to the purines. The same purines will occur in both the nucleic acids. When you take the pyrimidines, so the first one, an amino pyrimidine. So has amino group here. Second position, always it will have oxygen group. So 2, 6. This is called cytosine. So it is 2-oxo 4 amino pyrimidine. We have DNA and RNA. The next one usually occurs in RNA. This is uracil. This is 2,4 dioxo pyrimidine. This is usually RNA. And then we have the third one. Resembles uracil, only difference being there is methylation at this position. So this is thymine 5-methyl uracil or 2-oxo 2,4-dioxo 5-methyl pyrimidine. Usually occurs in DNA. So uracil usually occurs in RNA, thymine usually occurs in DNA. That's where the pyrimidines will make distinctions in terms of the nucleic acid. Purines will not make any distinction because both adenine and guanine, they will occur in both DNA and RNA.